Hello students, good morning. I am Professor Kiranar. I am from Department of Electrical and Electronics Engineering, the Anand Sagar Academy of Technology and Management, Bangalore. Today I am here to teach electrical circuit analysis. It is your third semester subject in electrical and electronic engineering. First, why we need electrical circuit analysis? First, we know the importance of electrical energy. Today we live in a predominantly electrical world. Electricity plays a very important role in today's life. We are in the era where without electricity we can't live our lives. Even we can't imagine our life without electricity because it will be in the dark. So first, electrical circuit analysis. Why we need circuit analysis? Circuit analysis is the foundation for electrical engineering. A deep knowledge in circuit analysis is required to handle electrical and electronic systems, power systems, etc. Electrical system or electrical circuit, it is nothing but the interconnection of the circuit components, and basically every electrical and electronic gadget forms a electrical circuit. In everyday life we see our electrical circuits or electronic gadgets or electrical gadgets. Wherever you see your electrical gadgets, it nothing but it consists of a electrical circuit. In this room I will take an example of laptop. This laptop is once again made up of electrical or electronic circuitry. So your laptop consists of basically monitor, CPU, everything. So everywhere monitor has some sub circuit, your CPU has some sub circuit, all combined will become a complex circuit. To handle our complex circuit, we need some kind of analysis or a tool which we will be calling it as electrical circuit analysis. Electrical circuit analysis is nothing but before that I will be telling you the course objective, why we will be reading all these electrical circuit analysis. It is nothing but to familiarize the basic laws. Basic laws are like Ohm's law, Kirchhoff current law or Kirchhoff voltage law. Next, about the some basic theorems like superposition theorem, reciprocity theorem or Norton's theorem, which will be using these laws or theorems to simplify our analysis. That is nothing but a mathematical analysis. In this course you will be also reading about a topic called resonance. Everywhere in this world you will be seeing about resonance. So we deal with electrical circuit and magnetic circuit and what are these topics related to resonance, and we will be also dealing with analysis of three-phase circuit. And apart from steady state analysis, we also deal with transient response of your circuits, which has DC analysis and also for AC analysis. And we have a very important mathematical tool, that is Laplace transform, which makes your electrical circuit analysis simpler. We will be reading all these objectives in this electrical circuit analysis. Today I am here to teach your first module. Your first module mainly consists of basic concepts. In basic concepts we will be reading about what are the types of elements, that is active and passive elements, and the sources, the types of sources, whether it is a ideal source or a practical source, or it is a dependent source or an independent source. Like this we will be reading about different types of sources. Once again, after sources we will be thinking about source transformation and source shifting, and this unit also concentrate on network reduction techniques, that is star delta transformation, or it may be a star delta transformation, or it may be a mesh and nodal analysis. Next, once after this session the student will be able to define what is electrical circuit or what is electrical network, what are the types of elements, whether it is an active element or a passive element, then what are the types of sources, whether it is an independent source or a dependent source, or it may be a ideal source or a practical sources. These are the session outcome of today's class. Then first I will come to electrical circuit or electrical network. An electrical circuit can be defined in a simple language, that is nothing but interconnection of electrical elements linked together in a closed path so that an electric current may flow. I will give you an example. So I have given a simple example here. So there is a closed circuit here which consists of a lamp which is energized by a battery. Whenever we want to call it as an electrical circuit, it should be a closed path. You can see here from positive it is given to the ammeter, from ammeter it is connected to the lamp, from the lamp it is connected to switch, and switch back to the battery. So it is a closed path. You can call it as a electrical circuit, or similarly it should have a multiple closed loop paths. In the other part of the circuit you can see here it has one voltage source and that is energizing multiple resistors. It has different electrical paths. There are multiple electrical paths or multiple closed circuit. So we can call this as a electrical circuit. once you know about electrical circuit, then we need to think about the before that I'll be giving a short glimpse on current and voltage. What is current? As everyone knows that current is nothing but the flow of charges, or you can also explain it as I is equal to dq by dt, which is nothing but rate of change of flow of charges across some surface. I will give you an example. It is something analogous to a pipe. In this pipe there is a flow of fluid. Fluid can be analogous to your electrical current. In this pipe there is a flow of fluid. This is something similar to your electrical current in terms of a wire. So the fluid will be analogous to current in your electrical circuit. We represent our electrical current with a terminology I. Similarly, voltage we also call it as electromotive force, or it is also called as potential difference. We represent voltage as V. So I'll give you an example. Once again, I'll take an example of a gravitational field. If you have a gravitational field like this, take an example of mass, the mass m. Whenever it left in a gravitational field, it is obviously that it will fall towards the earth because of your gravitational field. Similarly, in electrical field, if you have an electrical field and if you have a charge q, it will have a natural tendency to flow from one potential to the other potential. I'll call this potential as V1, the other potential it may be a ground, or you can also call it as potential V2. So whenever the current flows, there should be a potential difference. Always the current flows from, or the charge flows from higher potential to the lower potential. Whenever we call the term voltage, which is nothing but a potential difference. So what is voltage means? It is nothing but a movement of a charge of 1 coulomb from first terminal through the element to the second element, that is from one potential to the other potential. The flow of charges here, it is nothing but your electrical current, which is represented as ampere. 1 ampere means it is nothing but 1 coulomb of charge is transferred for within 1 second, that is called as 1 ampere. The force which is created to move the charges, that is nothing but your voltage, or we can also call it as electromotive force or potential difference. I think now you are comfortable with the basic terminologies, what is current and voltage. The next we will be thinking about our circuit elements. In circuit elements, we can classify it as active elements and passive elements. Active elements as the name indicates, it is nothing but it will be producing the energy. So the elements which have a capability to produce the energy are called as active elements. Once again, we can subclassify it as independent power sources and dependent power sources. I'll tell you in next slides what will be the independent power sources and dependent power sources. Similarly, passive elements, the elements which have a capability to dissipate the energy or which has a capability to store the energy are called as passive elements. Some of the examples are resistors, capacitors and inductors. Next, passive element, as I already stated that the element which receives energy or absorbs energy and then either converts it into heat or stored it in electric or magnetic field is called as passive elements. I'll take an example. These are the passive elements, that is resistor, inductor and capacitor. I'll take an example of resistor. You know the property of resistance. Resistance is nothing but the property of an element which opposes the flow of current. It is represented by the symbol R, and you know that R is equal to rho L by A, where L is length of the resistor and area is A is nothing but cross section area of your resistor, and the voltage and current in the resistor. So what will be the voltage across the resistor? V is equal to I into R, where V stands for voltage across the resistor, where I is equal to the current flowing through the resistor and R will be the resistance of that element. Similarly, if you want to find out the current flowing through the resistor from Ohm's law, we can write it as I is equal to V by R. This is the property of resistor, which is nothing but which opposes the flow of current. So, it is an passive element. How to justify passive element means it is nothing but it is dissipating the power in the form of heat, nothing but which is converting electrical energy into heat energy. So, we can call this as a passive element. It is not an active source, it is just a passive element, that is it is dissipating the power. So, we can call it as a passive element. Next, I will go with inductor. What is inductor? What is the property of inductor means? The property of inductor is nothing but it opposes the change in current, or it stores energy in the form of flux. Flux is nothing but here once again the magnetic field. The property of the inductor is nothing but it stores energy in the form of magnetic field. So, we know that the voltage across the inductor is given by V is equal to L into di by dt. That is nothing but the voltage across the inductor is given by directly proportional to rate of change of current, that is V is directly proportional to di by dt, and the proportionality constant here is L, where L is nothing but your inductance. The unit of inductance is Henry, or we represent it as H. Similarly, the current, how to find out current? The current flowing through the inductor is given by I is equal to 1 by L integral of V dt. The current flowing through the inductor is given by I is equal to 1 by L integral of V dt. We also know that the inductor has a property to oppose the change in current. So, once again we can call a term called XL. XL is nothing but inductive reactance. Inductive reactance is nothing but once again the opposition to the current. So, we can call it as XL is equal to 2 pi f L, or you can it also called as omega into L. 2 pi f is nothing but omega and L is nothing but your inductor. XL is called as inductive reactance. Similarly, next we will be reading about capacitor. So, capacitor, once again capacitor, the property of capacitor is to oppose the change in voltage. Also, the capacitor has a property which stores energy in the form of charge. Storing energy in the form of charge is nothing but here it is electrostatic field. As it is given there, the current flowing through the capacitor is directly proportional to rate of change of charge, that is I is equal to dq by dt, or you can also write it as I is equal to C into dV by dt, that is the current flowing through the capacitor. Similarly, if you want to find out the voltage across the capacitor, it is given by V is equal to 1 by C integral of I dt. These are the basic equations which governs the current flowing through the capacitor or the voltage across the capacitor. Once again, in terms of reactance, we call the capacitor association as capacitive reactance, and it is represented by Xc. Xc is nothing but 1 divided by omega C, or you can also represent it as 1 by 2 pi Fc. This is nothing but your capacitive reactance. This is so these are the governing equations of current flowing through the capacitor and the voltage across the capacitor. Also, Xc is nothing but the opposition to the flow of current, which is given as capacitive reactance. Next, I will speak about active elements. So, active elements, as already I explained, active elements are nothing but which supplies energy to the circuit, which means that it has a capability to generate energy or to supply energy. The examples of active elements, you can call it as a voltage source, a current source, or a generator. We all know that the generator has a capability to generate electricity. Similarly, we have taken an example like voltage sources and current sources. Once again, you can classify voltage sources. The voltage source, we already know that it will deliver energy with a specified terminal voltage which is independent of the current from the source, which means that, for example, if I take an example of 100 volts battery, it will continuously and constantly it will be delivering the 100 volts without any it is dependent on, which is independent of the current from the source, which means that it is not dependent on the current, always it will deliver 100 volts constant and continuously. So once again we can classify as time varying voltage source and time invariant voltage source. Example, a battery always it will deliver a constant voltage. With respect to time, if I draw, the voltage will be always constant with respect to time. So I call this as time invariant voltage source. Whenever you have a time invariant voltage source, we represent it like a battery. Similarly, we have one more kind of voltage source which is with respect to time varying voltage source. Time varying voltage source, we represent it as, this is also a voltage source, but which is time varying, means with respect to time the voltage will be varying. Next, similarly, current source. Once again, current source is nothing but it will deliver energy with a specified current, and it is independent of the voltage. Means if you represent a current source, if it has a capability to deliver 5 amps, it will constantly deliver 5 amps without it doesn't depend upon the voltage. So we have given the independent time variant current source and independent time variant current source, both are same. So which is invariant. Time invariant means the current will be constant with respect to time. These are the examples of current source. Next we have one more terminology called dependent source or controlled source. Here it may be a voltage source or a current source. It will be variable with respect to some other location. It may be a voltage dependent or current dependent. The source quantity may be a voltage source or a current source. It is determined by a voltage or current existing at some other location. Example, so these are the dependent sources. Once again we can classify it as voltage controlled voltage source and current controlled voltage source and current controlled voltage source. Similarly, we have voltage controlled current source and current controlled current source. What do you mean by voltage controlled voltage source? Means it is nothing but a voltage source, but it is dependent on some voltage somewhere in the circuit. Similarly, we have current controlled voltage source. Even this is a voltage source, but it is mainly dependent on the current flowing in the circuit or in some part of the circuit. Similarly, you can classify your current sources as voltage controlled current source and current controlled current source. So totally active sources I can classify it as ideal independent voltage source as shown in figure A. Similarly, the figure B, it is nothing but ideal independent current source. Then the third one, figure C, shows voltage controlled voltage source, and figure D represents current controlled voltage source, and the figure E represent voltage controlled current source, and figure F represent current controlled current source. You can see the symbol of current controlled current source. It is representing a current source where I is given by some constant D into IC. IC is nothing but somewhere the current flowing in one part of the circuit. Similarly, if you come to the figure D, where represents V is equal to some constant R into IC, where R indicates some constant and IC is nothing but your current flowing in the circuit. So it is a current controlled voltage source. These are the types of active sources. So once again I can classify it as ideal voltage source and practical voltage sources. So we all know that voltage source is nothing but it will be delivering the voltage, it will be delivering the energy at some specified voltage. Example, here I have shown. Here the x axis will be your load current I and the y axis will be your the voltage. So whenever you represent a battery, it should give a constant voltage with respect to current. The current has no influence on the voltage. The voltage should be constant throughout. But in ideal voltage source it is considered, but in practical world we won't get an ideal voltage source. So every element will be having some source resistance. So whenever in a practical voltage source, always the voltage dips as the current varies. So this is your practical voltage source, where you can see there is a voltage source in series with a source resistance. Due to this source resistance, there will be a dip in your voltage as shown in the graph. As current increases, there will be dip in your voltage, or there will be dip in your terminal voltage. Similarly, we will be having current source. Ideal current source means it should deliver energy with a specified constant current without any influence of voltage. Even though there is change in voltage, the load current should be constant. This is called as ideal current source, but practically we won't get any such current sources. There will be some source resistance across your current source. Always the load current I will dips because of your source resistance Rs in your current source. So we call this as a practical current source. In ideal current source, the load current will be constant throughout without any influence of the voltage. Even though there is change in voltage, it shouldn't disturb the current. But in practical current source, there will be change in current with respect to voltage. As voltage started increasing, there will be dip in your current. So we have represented the circuit. So there will be a current source in parallel with the source resistance, that is Rs. So now we can think about source conversion. Now we have read about voltage sources and current sources. So I'll take an example of a practical voltage source. What is practical voltage source? It consists of a battery or a voltage source in series with a source resistance. Similarly, if I take a practical current source, it is represented by a current source in parallel with a resistance Rs. So how to there is the term called source transformation, or we can also convert it as source conversion, which means that any voltage source with series resistance Rs can be converted into equivalent current source, which is represented by I in parallel with the resistance Rs. Or similarly, you can convert a practical current source. A practical current source is nothing but a current source in parallel with the source resistance can be converted into equivalent voltage source, that is V in series with the resistance, internal resistance Rs. With the application of our Ohm's law, we can convert our practical voltage source into practical current source, where I is given by, according to Ohm's law, I is equal to V by R. Similarly, the source resistance of your practical voltage source and current source will be same, or you can convert the equivalent practical current source into voltage source. Once again, the same application of Ohm's law, where V is equal to I into R. This is nothing but either you can convert a practical voltage source into practical current source, or practical current source into practical voltage source. This is called as source transformation. So I have given you, to convert a voltage source into current source, it is given by Is is equal to Vs by Rs, which is nothing but your Ohm's law. I is equal to V by R. Vs is nothing but your source voltage and Rs is nothing but your source resistance. Similarly, you can convert back a current source to a voltage source, which is nothing but Vs is equal to Is into Rs. That is nothing but you can convert your current source to a voltage source. So we will take an example. We have a voltage source which is of 10 volts and which has a source resistance of 2 ohms. If you want to convert it into equivalent current source, then the formula is I is equal to V by R. The value of your current source is given by I is equal to 10 by 2, which is nothing but 5 amps. So whenever you are converting, the value of your current source now will be equal to 5 amps. The value of your source resistance will be same as that of your voltage source. Here the value given here is 2 ohm. So the value in your practical current source will be equal to 2 ohm. Similarly, you can convert a current source into a voltage source, where I'll take an example where I is equal to 20 amps and the resistance, the source resistance is given by 5 ohm. If I want to convert it into equivalent practical voltage source, then we know the formula V is equal to I into R, where V is equal to the value given I is equal to 20 amps into the resistance given there is 5 ohm. The voltage will be equal to 100 volts. The voltage will be equal to 100 volts. Similarly, what will be the source resistance in your practical voltage source? When you are converting it from current to voltage, whatever the source resistance in current source will be equal to the resistance in your practical. So, here it is given as 5 ohms. So, in your voltage source also it will remain same, that is nothing but 5 ohm. So, I think now you are familiar with how to convert a voltage source into a current source or vice versa, that is nothing but current source to a voltage source. This is called as source transformation, or we can also call it as source conversion. Next, similarly, we know how if the resistance are connected in series, what will be the equivalent resistance, and if the resistance are connected in parallel, how to evaluate that. Those things it is very important in electrical circuit analysis. So, the basics for electrical circuit analysis, we need to know what is Ohm's law, what is Kirchhoff current law, voltage law, how the resistance will behave, or what is the property of inductor and capacitor. When it is connected in series, what will be the effect, or when it is connected in parallel, what will be the effect. With the complete in-depth knowledge, then we can handle electrical circuit analysis. For example, if we know that we represent resistance as R, if two resistors are connected in series, R1 and R2, the effective resistance or the equivalent resistance is given by R equivalent is equal to R1 plus R2. That is nothing but n number of resistance. If it is connected in series, then it will be equal to the summation of all, that is R1 up to Rn. If n number of resistors are connected in series, then we need to summate all the resistance value. Similarly, if the resistances are connected in parallel, I will take an example here, R1 and R2. This R1 and R2 are connected in parallel. If you want to evaluate the equivalent resistance, it is given by 1 by R is equal to 1 by R1 plus 1 by R2. That is nothing but the reciprocal of effective resistance or equivalent resistance will be equal to summation of reciprocal of individual resistance. That is 1 by R equivalent will be equal to 1 by R1 plus 1 by R2. Like this, if there are n number of resistance connected in parallel, then it will be equal to the summation of reciprocals, that is 1 by R1 up to 1 by Rn. Now, I think you are familiar with how to handle with series and parallel circuits. Next, we will think about the voltage division principle. What is voltage division principle? For example, I will take a circuit here which has two resistances connected in series. Here I call it as the voltage source V, and the resistance is given by R1 and R2. What is the current flowing here? According to Ohm's law, I is equal to V divided by R1 plus R2. That is nothing but the total current flowing in your circuit will be equal to I is equal to V divided by R1 plus R2. For example, if there is a question, if you want to find out the drop across R1, which means that if you want to measure the voltage across R1, so you need to voltage across R1, or if you are placing a voltmeter between across R1, so what should be the voltage? To determine that, so what will be the voltage across R1? VR1 is nothing but the drop across resistance R1. What do you mean by drop? Drop is nothing but I into R1. What is the total current flowing in your circuit? Which is nothing but I is equal to V divided by R1 plus R2. So, you can represent it as V into R1 plus R2 multiplied with R1. So, this is the formula if you want to determine the voltage across the resistance R1, that is VR1 will be equal to V into R1 divided by R1 plus R2. In simple terms, if you want to tell, the total voltage into same resistance divided by the total resistance. If you want to find out the drop across R1, the total voltage into the same resistance, that is R1, divided by total resistance, that is R1 plus R2. Similarly, if you want to find out the drop across R2, that is nothing but VR2. If you want to find out VR2, the formula is total voltage into same resistance divided by summation of total resistance, that is R1 plus R2. This is called as voltage division principle. So now we'll take an example where the voltage source is of 10 volts and we have two resistors connected in series. I'll take it as one as 1 ohm resistor, the other one as 2 ohm resistor. Now I need to find out the drop across resistance R1 or the drop across resistance R2. The drop across resistance R1, that is nothing but VR1. What is the formula? The formula here is total voltage into same resistance, that is R1, divided by total resistance, that is R1 plus R2, which is nothing but the total voltage given in this question is 10 volts into R1. R1 is nothing but 1 ohm divided by the total resistance, that is nothing but 1 plus 2, which is given by 10 by 3 volts, or you can approximately write it as 3.33 volts. Similarly, if you want to find out the drop across resistance R2, VR2 is given by once again the total voltage, which is nothing but 10 volts into the same resistance. The resistance value is 2 ohms divided by the total resistance, which is 1 plus 2, which is nothing but 20 by 3 volts. This is the drop across the resistance the resistance R2. This is also called as voltage division principle. Next we will be concentrating on current division principle. Current division principle. Current division principle. So current division principle means we need to determine what is the current flowing through resistance R1 or what may be the current flowing through resistance R2. So first thing, how to determine the current flowing. So we know that Ohm's law, once again, I is equal to V by R. So the current flowing I1 will be equal to V divided by R1. Similarly, what will be I2? I2 will be equal to V divided by R2. So you know how to calculate I1 and I2. What is your total current IT? Total current IT will be equal to I1 plus I2. So you know that I1 is equal to V by R1 and I2 is equal to V by R2, or you can also represent this equation as V is equal to I1 R1 and here V is equal to I2 R2. I will call this as equation 1 and equation 2. So equation 1 and equation 2 tells that V is equal to I1 R1 and equation 2 states that V is equal to I2 R2. So we can equate both the equations. So it will become I1 R1 will be equal to I2 R2, or we can also write I1 is equal to I2 into R2 by R1. This I will call this as equation 3. This I will call this as equation 4. The total current I total is given by I1 plus I2. We also know that from equation 3, I1 is equal to I2 into R2 by R1. Substituting equation 3 in equation 4, we get I total is equal to I2 into R2 by R1 plus I2. If I take I2 common in this equation, it will become R2 by R1 plus 1, which is nothing but I total will be equal to I2 into R2 plus R1 by R1, or I2 in terms of I2, if I write this equation, I2 will be equal to I total into R1 divided by R1 plus R2. For example, in this circuit, the direct procedure is, if you want to find out the current flowing through the resistance R2 is given by I2 is equal to the total current I total into R1 divided by R1 plus R2. Here I have taken an example of voltage source. Similarly, if I consider a current source, so this I will be equal to I total. So from this you can calculate the current flowing through I2, that is nothing but total current IT into the opposite resistor, that is R1, divided by summation of both the resistance. Similarly, if you want to find out I1, the rule here is the total current IT into opposite resistance. The current flowing through R1 is I1. So if you want to find out I1, then you need to consider the opposite resistance. Here the opposite resistance is R2. I total into R2 divided by R1 plus R2. If you want to find out I2, then it will be total current into opposite resistance is R1 divided by R1 plus R2. This is called as current division principle. Whenever you have a parallel circuit, you need to consider the current division principle, and whenever you have a series circuit, if you want to find out voltage, then it will be a voltage division principle. Once again I will summarize the voltage division principle and current division principle. If you want to find out the drop across any resistor in a series circuit, if I consider it as VR1, then it will be equal to total voltage into same resistance divided by total resistance. Or if you want to find out VR2, then it will be equal to total voltage into R2 divided by summation of the resistance. This is called as voltage division principle. Similarly, if you want to know current division principle, then it will be I1 will be equal to total current into opposite resistance. Opposite resistance here is R2 divided by summation of total resistance. Similarly, if you want to find out I2, then it will be equal to I total into R1 divided by R1 plus R2, that is the current flowing through resistance R2 is given by total current into opposite resistor. Opposite resistor in this circuit is R1 divided by R1 plus R2. This is called as current division principle. So today in today's session we read about what is electrical circuit and electrical network. Once again I'll give an explanation. Electrical circuit is nothing but interconnection of electrical elements. It should be a closed path. Example is, if there is a voltage source, it should have a closed path. This I can call it as a electrical circuit. Whichever electrical gadgets or electronic gadgets, wherever you go, you can see your electrical circuit. To analyze our electrical circuit, we need electrical circuit analysis. And what is electrical circuit means? It is nothing but a interconnection of electrical elements, and it should form a closed path. Closed path, you can see here, it is a closed path. So this is V voltage source. I'll take R1 and R2. This is an example of your electrical circuit. Next we think about active and passive elements. We thought about active and passive elements. What is active elements? Active elements are nothing but which has a capability to deliver or to produce energy. Examples are nothing but your voltage source, or it may be a current source, or it may be a generator. These are the examples of your active elements. Similarly, passive elements. Passive elements means which has a capability to dissipate energy, or which has a capability to store energy in the form of electromagnetic field or electrostatic field. The examples of passive elements are your resistor, or it may be a inductor or capacitor. We have already learnt the governing equations of your inductor and capacitor. What will be the current flowing through the inductor and what will be the voltage across the inductor. We have learnt all those things. Next we read about ideal and practical sources. What is ideal source means? Which doesn't depend upon your, if you take an example of ideal current source, it has a capability to deliver constant current without any effect of your voltage. Even though there is change in voltage, the current will be constant throughout. But practical sources means it consists of a source resistance. If you take a current source, then there will be a source resistance across your current source. Similarly, in ideal voltage source, it will deliver a constant voltage. In a practical voltage source, there will be a source resistance in series with your voltage. So next we learnt about dependent source and independent sources. Whatever the voltage source here shown, here it is nothing but independent. It is not dependent on any circuit parameters. But dependent sources means it has a capability. So here I am showing an example of voltage dependent voltage source. It can deliver a voltage V and it is dependent on Vx. Vx is nothing but the voltage in your circuit at some point. Similarly, we have a current source. It may be dependent on, even in your current source, it may be a current dependent voltage source or voltage dependent current source. Like this we have dependent sources. Then we learnt about source transformation. Source transformation is nothing but converting a practical voltage source into equivalent current source, or vice versa. That is nothing but a practical current source into a practical voltage source. In next session I will be teaching about source shifting. In today's session, we have learnt about the circuit, active and passive elements, practical sources, dependent and independent sources. We have learnt about source transformation. In next class, we will be dealing with few problems on source transformation, and I will be teaching a concept called source shifting. Thank you very much.